our last talk today by Carlos Galeano-Rios is a model for the impact of a superhydrophobic sphere onto a bath and application to bouncing droplets.
Thank you. Well, thanks to the organizers. It's a very special feeling for me to be back at IMPA as a visitor now. I spent more than 6 years of my life here, so this still feels like home somehow. So I'll be talking about a bit of work that we've done partly during my PhD when I was a PhD student here, but also during my current postdoc at Bath. So the physical problem that we're modeling is this one. So you see here there is a tiny ball which is coated in a superhydrophobic, with a superhydrophobic coating. And in fact, this ball is heavier than water, so it's denser than water. It should sink, but it floats by virtue of the superhydrophobic coating. And also notice that this impact generates surface waves that can be clearly seen to travel across the surface. So we were interested in this problem, and we came across with this experimental report on the impact of superhydrophobic balls. So in 2008, this paper was published, and Lee and Kim studied different cases, among them some in which the superhydrophobic ball falls onto the free surface and sometimes sticks to it and stays oscillating, and other times it actually bounces off the surface. Right? So they also come up with a model in this work. You can see here the black points are experimental data that they recover from these experiments, and their model predicts the initial and final stages of these rebounds. But as they claim themselves, it comes apart during the middle part of the rebound. So we were trying to model this, and we developed an approach. Basically, we start from first principles of fluid and particle mechanics, and we naturally add some asymptotic simplifications for these regimes, and we obtain a reduced model for the behavior of these systems. So essentially, we just impose simple natural kinematic constraints, saying that the two masses cannot occupy the same space, and some geometric conditions on the contact area and its boundary. I will show that more carefully. So the tricky bit of this is that we need to resort to singular integrals to solve the problem. So I'll show a little of that. Right, and this is joint work with Paul Milewski and Jan-Mark van den Broek. So our fluid surface behaves essentially according to these equations, where eta is the free surface elevation. We have horizontal Laplacians, curvature operators. We have a velocity potential given by phi. And we have this n operator, which is the Dirichlet-Neumann operator, which is given by this expression in the linear case, in the case of linear waves. Right? So this is a singular integral, which is taken in the Cauchy principal value sense. Right? The approach is basically to look at the solid ball as a sphere that doesn't deform, which, while impacting the free surface, will have a contact area. Throughout that contact area, the free surface will match the surface of the ball. This separation that appears here is, it serves purely descriptive purposes. It's in the model, these two surfaces should coincide. And we also impose that the fluid surface, once it's detaching from the solid, so at the boundary, at the contact area, there should be tangency. So the free surface should have the slope of the sphere at that point. So, and of course, we just use Newton's second law for the vertical motion of the ball. Right, so we then end up with this system where we have an equation for the free surface, the velocity potential, which includes a term for the pressure on the free surface, which is the physical element that relates the motion of the ball with that of the free surface. So we also know that we have this restriction, so the free surface can never be above the sphere. So that's what I meant by saying that we impose natural kinematic and geometric constraints. And we also impose tangency at the boundary of the contact area. We also start from a quiescent path. Okay, so the main challenge perhaps is to find a numerical approximation for this operator. So singular integrals are operators that rely a lot on cancellation properties. So you have to be very careful about how you treat this calculation. So we're dealing with a sphere impacting a path that's initially quiescent. That means that our waves will be axisymmetric. And our kernel is also axisymmetric, but it's axisymmetric around a different center. So we have to use two different meshes. So there's a radial mesh here shown in black and a polar mesh here shown in gray. And we have to carefully integrate the kernel. So we try to always integrate the kernel exactly and approximate the function that's being evaluated by the operator. So this gives surprising results for a linear theory. So you can see here in this picture, our predictions are shown in black. So black is the position of the simulated ball, and gray in the back, almost coinciding, except perhaps at the very end, is the experimental report by Lee and Kim. So this, if you recall, was their experimental measurements and their model predictions in solid lines. And this is what we get for the same parameter regime. So the crosses here correspond to the bullets here. The black line is, both black lines correspond to the center of the ball, but our model predicts the full rebound. This is just the south pole of the ball, and this is the free surface of the fluid. So this is a video of that simulation. So again, in gray in the back, it's the experimental measurement for the same initial conditions. Right, so the surface is deformed substantially, which might make you think that a linear theory would get a terrible result. And it doesn't seem to be the case. So we were gladly surprised by this. Yeah. So, yeah, well, there is indication that we need nonlinear terms to recover the energy properly. So it's probably losing more energy than it should. So we've been working more on this. I'll show that later on. Yeah, I was surprised to see this. So here's another video. This is nicer to look at. But I'm still comparing the two of them. You can also see the trigger waves, how they propagate. The sudden change in color is not precisely a change in color. It's the experimental ball coming above the other one. So I'm comparing both of them. We just lost some amount of experimental data there because they only track the rebound so far. So you can see there it changes color when it's coming back up. Just about there, because it's rebounding faster. Okay, so we have this model, and we said, how about we revisit this problem that we've been working on? So I'll be reviewing some of the stuff that Andre has already told you. So some of you heard his talk, some of you might not. So I'll just go really fast over what bouncing droplets are. Okay, so first of all, the Faraday instability will be very important in this problem. So we have a container of fluid which is being shaken with a constant frequency and increasing amplitude. And when threshold value of amplitude is reached, the free surface will become unstable to a field of standing waves. So just keep that in mind for a second. And independently, let's consider again, the video of the droplet hitting the fluid. There's no shaking here. And you can see that it takes some time for the droplet to coalesce with the underlying bath. And we're going to combine these two phenomena, and we're actually going to inhibit droplet coalescence. So just again, look at how it takes some time for the droplet to coalesce. And what was achieved combining these two phenomena is if you shake the bath, you provide the possibility for this air layer that's separating the droplet and the fluid bath to replenish, and so coalescence is inhibited, and you can obtain this novel object, which is being called a bouncer, which can have different bouncing states, different periods of bouncing, and as is reported by the experimentalists, this state can be held for weeks even. So this is already a very interesting object. It's basically the connection of a surface wave with a particle-like object. And so someone had the idea to explore it more and found even more interesting things. So in a certain parameter regime, it will become, this bouncing droplet will become unstable to lateral perturbations and will start a horizontal trajectory spontaneously. So now we have a particle-like object, which is the droplet, and a wave that are moving together. And so Yves Couder had the brilliant idea to have this particle wave associations run through single and double slits, reproducing some of the famous quantum experiments. A lot of curious dynamics arises, not only the interference and diffraction patterns, but also, and I would say these are probably the nicest ones, interactions between walkers, right? So there is a kind of analog of an exclusion principle, because these droplets will orbit each other at predetermined radii, which are related to the wavelength of the Faraday wave. And so, as I said, we were trying to revisit something that we did before. So during my PhD at IMPA, I worked with Paul Milewski and Andre and John Bush, and we published this paper where we presented a model in which we generated the waves by this pressure on the free surface. But we were still using a non-linear spring model to compute the droplet surface interaction. So now that we have a different model for impacts on free surface, we said, how about we revisit it? So just to give you an idea, we were able to recover a lot of the dynamics. So we were capable to recover many of the bouncing modes, so different periods of bouncing of this bouncing droplets. We had phase diagrams that agreed reasonably well with experiments, and we could also recover features of the wave field of this bouncing and walking droplets, even quantitative comparisons with wave field measurements. So we wanted to, let's not forget the droplet-droplet interaction, which we also got there. So at least we want to recover with this new solid surface interaction model our bouncer dynamics. And just to give you an idea, we used to have a model for droplet motion which relied on this spring model where there are some constants here, and they come from the work of Molecek and Bush. They obtained these constants from fitting some experimental curves determining things like coefficients of restitution and so on, Right? We wanted to see if we could recover all this dynamics just resorting to our model of solid surface interaction. And so we went ahead and decided that this droplet won't deform in this model and imposed this kinematic matching method, and we did obtain good results. So you can see now that the bouncing droplet is acting as the generator of waves, but the surfaces are made to coincide because before, when we had a spring model, they didn't necessarily match each other. I mean, the two surfaces didn't coincide necessarily. And perhaps more importantly, now we have no parameters that are provided from experiments. So we derive this basically just from simple assumptions and first principles. We can reproduce bouncing modes just like we did. We have phase diagrams that do very well with, in comparison with experiments. And I'm particularly happy with this picture, which is hard to understand perhaps, but let me try to explain it clearly. So this is for one single droplet. The whole graph is for one single droplet, but the shaking amplitude is being increased in the horizontal axis. So this is very little shaking, and this is very high shaking. And the time increases in the vertical direction, and it's measured as the phase of the sinusoidal shaking. So the lines are from our simulations, and the background coloring corresponds to experimental measurements. So the droplet is always in flight at the very beginning, so at the very below in the down below in the graph, and as time increases, it eventually touches down as it reaches the black curve in our simulations, or the shaded region in experiments, and it flies off again when it reaches the blue curve or the shaded region. So, as I said, there is no feedback between experiments and our modeling. Yeah, you have a question? Oh, uncertainty. So they have some standard deviations of their measurements because they measure several periods of bouncing. So yeah, so that's why I went with shading, not a line. Yeah, that's correct. So experimentally, it's much easier to determine impact than takeoff, because at impact there is a trigger wave, and at takeoff, basically, not. Okay, so we are continuing to work on this because we want to model walkers. That will take some special effort, so we're going to have to adapt something that so far is axisymmetric for a non-axisymmetric setup, but we're working on that. We also want to work with walkers approaching submerged barriers. So we're working with Matthew Duray, a PhD student at Bath, with this, and of course Paul and John Mark. And there's also this collaboration with Daniel Harris from UNC at Chapel Hill, who is a very talented experimentalist and fortunately is willing to redo many of his experiments, do a big parameter sweep, so we can study better how and why we're making errors, for example, at the rebound. And as I said, perhaps it has to do with the nonlinearities that we're throwing out. Just to show you how much these impacts can be different from each other, this is a different impact, and the rebound is a lot stronger. We do naturally better for impacts that are not as hard as the second one. Our model predicts this much better than this. Right? So this is a preliminary result. So again, the shaded region is experimental. So again, there's an uncertainty in measurement. The black curve is our prediction for the same thing. And so we are over-predicting time of contact and under-predicting the coefficient of restitution. Okay? But well, we're still working on improving this. Okay, well, thank you.